Right now, as you read these words, you are hurtling through space at a speed that would carry you from one side of the United States to the other in under 20 seconds. Not on a rocket, not aboard any spacecraft. Simply by existing on the surface of this planet, which is itself orbiting the Sun, which is itself orbiting the center of a galaxy so vast that the number of stars it contains exceeds the number of grains of sand on every beach on Earth. You are moving. You have always been moving. And the galaxy you are moving through is so incomprehensibly large that everything humanity has ever explored, every mission, every probe, every telescope pointed at the sky, amounts to less than a single step in a journey that would require millions of lifetimes to complete. You have almost certainly seen a diagram of the Milky Way, the kind that appears in textbooks, on the walls of planetariums, in the opening frames of space documentaries. A bird's-eye view of a great spiral, arms sweeping outward from a glowing center, colors shifting from orange and yellow at the core to blue and white along the outer edges where new stars are being born. And somewhere on one of those arms, usually tucked between two of the larger, more impressive-looking features, there is a small label. It might say Orion Arm, it might say Local Spur, it might simply say, "You are here," with an arrow pointing to what appears to be a thin, unremarkable bridge of material connecting two grander structures. You look at it, your brain registers it as small, and you move on. But here is what those diagrams have never told you. That sliver, that modest-looking connector that your eye passes over on its way to the more dramatic features of the galaxy, is so physically enormous that light itself, traveling at 300,000 kilometers every single second, would need 10,000 years to cross it from end to end. The structure your brain dismissed as a minor footnote on a galactic map is larger than the entire span of recorded human civilization, measured not in years but in the distance light travels during that time. The Orion Arm is not small. It only appears that way because the objects surrounding it on those diagrams operate at a scale so extreme that even something 10,000 light-years long looks like an afterthought by comparison. Tonight, that misperception ends. If you find yourself drawn to journeys like this one, explorations that take the universe seriously and refuse to flinch at the numbers, consider hitting the like button and subscribing. It is a small gesture, but it keeps this kind of work alive. Now, make yourself comfortable. Clear your mind of everything measured in kilometers and hours and years. What comes next requires a different kind of thinking entirely. Let's begin. To understand the Orion Arm, you first need to understand the galaxy it belongs to. And to understand the galaxy, you need to confront an obstacle that astronomers have wrestled with for centuries. We are inside it. Every observation we make, every measurement we take, every map we draw of the Milky Way is made from a position embedded within the structure we are trying to describe. No human being has ever seen our galaxy from the outside. Every image you have ever encountered of the Milky Way as a complete object seen from above, its spiral arms laid out in full, its center glowing with ancient starlight, is an illustration, a reconstruction, an educated artistic interpretation built from data gathered by instruments that have never left the galaxy's plane. Think about what that means practically. Imagine you are standing inside a vast forest. Trees surround you in every direction. You can see the trees nearby clearly. You can make out the shapes of trees a little farther away. In the distance, the trunks blur together into a continuous wall of bark and shadow. You cannot see where the forest ends. You cannot tell whether it is round or elongated, whether it has clearings at its center or dense thickets, whether it is symmetrical or irregular. You are inside it, and being inside it is precisely what prevents you from seeing it whole. That is the situation astronomers find themselves in when studying the Milky Way. They are standing in the forest, and the forest is 100,000 light-years across. What patient, ingenious observation has revealed over the past century is this: the Milky Way is a barred spiral galaxy. That classification contains several distinct structural elements, each of which contributes to the overall architecture of our galactic home. At the center sits the galactic bulge. This is a dense, roughly spheroidal concentration of predominantly older stars, packed far more tightly than the stars in our region of the galaxy. The bulge spans roughly 10,000 light-years across its widest dimension. If you were to find yourself on a planet near the galactic center, the night sky would bear no resemblance to the one visible from Earth. Stars would crowd the darkness in numbers and brightness that would make our own sky seem sparse. Many of them would be bright enough to cast faint shadows on the ground. The sky would never fully darken. There would be no true night. Running through the heart of this bulge is the central bar. This is the feature that earns the Milky Way the bar designation in its classification. A bar-shaped concentration of older, redder stars cuts through the galactic center like a beam of light frozen in place. Estimates of its length vary depending on the method used to measure it, but most studies place it at somewhere around 27,000 light-years from end to end. It is not a solid structure in any conventional sense. It is a region where the density of stars is elevated, a gravitational pattern that has persisted for billions of years, shaping the orbits of the gas and stars around it. Extending outward from the ends of this central bar are the spiral arms. These are the features that define the visual character of the Milky Way and of spiral galaxies in general. When you see those famous photographs from the Hubble Space Telescope or the James Webb Space Telescope, the face-on images of distant galaxies with their sweeping luminous arcs of blue and white, the structures you are admiring are spiral arms. The Milky Way has them. We simply cannot photograph our own from the outside. Before going further, it is worth addressing a misconception that surprises most people when they first encounter it. Spiral arms are not solid structures. They are not physical walls of stars orbiting together as a unit. If they were, they would have wound themselves into oblivion long ago. The inner regions of a galaxy rotate faster than the outer regions, a phenomenon called differential rotation. A solid arm would be twisted tighter and tighter with each successive orbit until it wrapped around itself and disappeared entirely. And yet spiral arms have persisted across billions of years of galactic history. Something else must be responsible for their existence. That something is a density wave. The concept is easier to grasp with an analogy. Consider a long stretch of highway during heavy traffic. Somewhere ahead, the road narrows, or an obstruction causes vehicles to slow. A jam forms. Cars entering the back of the jam reduce their speed, travel through the congested region, and then accelerate again on the other side. The individual cars are always moving forward, but the jam itself remains roughly stationary. It is a pattern, not a collection of specific vehicles. The jam exists because of how the cars interact with that region of the road, not because particular cars are stuck in place. Spiral arms work by the same principle. Stars, gas clouds, and dust drift through the galaxy on their respective orbits. As they enter a region where the gravitational field creates a compression, they slow slightly, bunch up, and then continue on their way. The compression zone is the arm. It persists as a stable pattern even as the individual stars pass through it. Within this zone, gas clouds are squeezed with enough force to trigger gravitational collapse, and new stars are born. The youngest, most massive, most brilliantly luminous of these stars, the hot blue giants that burn through their fuel in mere millions of years, light up the arm from within, marking its location with intense radiation. These are the stars that make spiral arms visible in photographs of distant galaxies. The arms glow blue because they are continuously producing these short-lived stellar giants. The interarm regions appear redder and dimmer because they contain older, cooler stars that formed earlier and have had time to age. The Milky Way possesses several of these arms. The Perseus arm is one of the two major features in our region of the galaxy. It lies outward from our position, farther from the galactic center, curving around the galaxy in a long arc that extends for tens of thousands of light years. The Sagittarius Carina arm lies inward from us, between our position and the galactic center. When you look toward the constellation Sagittarius on a summer night, you are gazing roughly in the direction where this arm lies between us and the core. Beyond these are the Scutum Centaurus arm, which many studies identify as the largest and most massive arm in the entire galaxy, and the Norma arm, positioned even closer to the galactic center. Farther out than the Perseus arm In the sparse outer reaches of the galactic disk lies the outer arm, a more diffuse feature extending into the galaxy's thinning periphery. The exact number of arms, their precise lengths, the question of whether certain features are full arms or branches, all of this remains an active area of research. Mapping the interior of something you inhabit, using only the observations you can make from a single fixed point within it, is an exercise in painstaking inference. The picture has been revised repeatedly over the decades as new instruments and new techniques have produced sharper data, but the broad architecture is settled. The Milky Way is a rotating disk of hundreds of billions of stars, structured into sweeping arms that spiral outward from a barred center, the whole assembly turning slowly around a point occupied by a supermassive black hole with a mass approximately 4 million times that of our Sun. That black hole is called Sagittarius A star. At this moment, it sits roughly 26,000 light-years from where you are. 26,000. Light, which covers 300,000 kilometers in a single second, would require 26,000 years to travel from your current location to the galactic center. When that journey began, the last ice age still had thousands of years remaining. Agriculture would not exist for another 10 millennia. Every civilization, every city, every written word, every structure humanity has ever built, all of it would unfold and conclude well before a beam of light sent from Earth today could complete the trip to the heart of our own galaxy. And that is how far we are from the center of the Milky Way. Not from a distant star, not from another galaxy, from the center of the galaxy we live in. Our position within this structure places us roughly in the inner edge of the Orion Arm, the feature whose true scale is the subject of everything that follows. The Sun sits in this region, and it has been orbiting the galactic center for approximately 4.5 billion years. During that time, it has been moving at a speed of roughly 230 kilometers per second. At that speed, you could circle the entire Earth in under 3 minutes. And yet, even at 230 kilometers per second, the Sun requires somewhere between 225 and 250 million years to complete a single orbit of the galaxy. 1 full galactic year. The last time the Sun occupied approximately its current position in its orbit, the first dinosaurs were only beginning to appear on Earth. The time before that, the ancestors of virtually all modern animal groups were just beginning to diversify in the seas. Earth has completed roughly 20 laps around the galaxy since its formation. 20 orbits in 4.5 billion years. And on each of those orbits, the Sun has been drifting through the galaxy's landscape. Because spiral arms are density waves, rather than fixed structures, stars move through them over geological timescales. The Sun has probably passed through multiple arm regions over its lifetime. It has spent time between arms, in the quieter inter-arm zones, where gas is thinner and star formation less active. Right now, by the reckoning of the cosmic calendar, we happen to be in the Orion Arm. This matters more than it might initially seem. The location of a star system within a galaxy is not merely an address. It has consequences for what that system experiences over time. The major spiral arms are regions of intense stellar activity, prolific star formation, and frequent supernova explosions. The massive stars born inside those arms burn brilliantly and die violently, releasing enormous bursts of radiation that could prove hazardous to any nearby planetary system attempting to sustain complex life over billions of years. The Orion Arm, by contrast, is quieter. Its star formation rate is lower, its supernova frequency is reduced. The stellar environment here is calmer, more stable, more forgiving of the patient, slow processes that allowed life to emerge and persist on Earth across 4 billion years. Some researchers frame this in terms of the galactic habitable zone, the idea that certain regions of a galaxy are more hospitable to life than others. Too close to the galactic center, and the density of stars, the frequency of supernova, and the intensity of radiation create a hostile environment. Too far from the center, in the galaxy's outer reaches, and the relative scarcity of heavier elements, those forged inside stars and scattered by their explosions, may mean there is insufficient raw material to build rocky planets with the chemical complexity life appears to require. The Orion Arm, positioned at a middling distance from the center, in a relatively tranquil secondary feature, may occupy something of a sweet spot. Not so active that life is perpetually disrupted, not so sparse that the ingredients for life are absent. This is the stage on which human existence has played out. A barred spiral galaxy 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, all of it organized into arms and spurs and interarm voids, all of it slowly rotating around a supermassive black hole at its heart. And within that entire structure, we are here, in the Orion Arm, in the quiet, secondary feature, between two of the galaxy's grand spirals, on a small rocky planet orbiting one ordinary yellow star somewhere along the arm's inner edge. The diagrams have always shown you this picture, but they have never shown you what it truly means. They have given you the address without conveying the scale of the territory it describes. And the scale, as you are about to discover, changes everything. Now consider what you have just learned. You live inside a barred spiral galaxy, 100,000 light-years across. Your sun orbits the galactic center at 230 kilometers per second and still requires 250 million years to complete one lap. The structure you inhabit, the Orion Arm, sits between two of the galaxy's major spiral features, positioned roughly 26,000 light-years from the galactic core. You have seen this picture on diagrams your entire life, and every single time you looked at one of those diagrams, your brain lied to you. Not through any failure of intelligence, not through carelessness or inattention. Your brain was doing exactly what it evolved to do, which is interpret visual information quickly and efficiently, using the assumption that the sizes of things on a page reflect the sizes of things in reality. It is a reasonable assumption for almost everything your ancestors ever needed to understand. A large animal drawn large on a cave wall was, in fact, a large animal. A distant mountain drawn small was, in fact, smaller in apparent size than a nearby hill. Visual proportion has served our species extraordinarily well for hundreds of thousands of years. But galaxy diagrams are not maps in any sense your visual system was built to interpret. They are compressions. Violent, extreme, information-destroying compressions of distances so vast that no medium available to human hands can represent them honestly. When an illustrator sits down to draw the Milky Way on a page, they face an impossible problem. The galaxy is 100,000 light-years across. The page is perhaps 30 centimeters wide. Every centimeter of that illustration must therefore represent approximately 3,300 light-years of actual space. Every millimeter represents 330 light-years. Every fraction of a millimeter contains distances that no human technology could cross in any number of generations. Your eye looks at the resulting image and sees a grand central structure, sweeping major arms, and then, tucked between two of those arms, a small connector, a bridge. A thin feature that barely registers before the eye moves on to something more visually impressive, and your brain, faithfully applying its evolved heuristics, concludes that thing is small. It is not small, it is 10,000 light-years long. Let that number sit for a moment before we try to make it mean anything. 10,000 light-years. 1 light-year is the distance light covers in a full year of continuous travel at 300,000 kilometers per second. That works out to approximately 9.46 trillion kilometers. 1 light-year, 9.46 trillion kilometers. Now multiply that by 10,000. The number that results is so large that writing it out in kilometers would produce a figure with 17 digits. There is no comparison in ordinary human experience that makes a 17-digit number of kilometers feel real, so let us approach it differently. The nearest star to our Sun is Proxima Centauri. It sits approximately 4.24 light-years from Earth. Just 4, not 10,000. 4. And the fastest spacecraft humanity has ever built, the Parker Solar Probe, which, at its closest approach to the Sun, reaches speeds of roughly 192 kilometers per second, would require approximately 6,800 years to reach Proxima Centauri. That is longer than the entire span of recorded human civilization. If a spacecraft had been launched toward our nearest stellar neighbor on the day the first cities were being founded in ancient Mesopotamia, it would still be en route right now, with thousands of years of travel remaining ahead of it. That is 4.24 light-years. The Orion Arm is 10,000 light-years long. If you could somehow travel at the speed of light, which the laws of physics categorically forbid for any object with mass, the crossing would still take 10,000 years. 10,000 years ago, agriculture was in its infancy. The first experiments with cultivating crops were just beginning in the Fertile Crescent. Stonehenge would not be constructed for another 5,000 years. The Egyptian pyramids were still 8,000 years away from being built. Writing had not yet been conceived. Metalworking was unknown. The wheel had not been invented. Human beings were living in small nomadic and semi-nomadic groups, tracking animal migrations, gathering wild plants, and chipping stone into tools. If you had set out from one end of the Orion Arm at the speed of light at that exact moment in history, at the very threshold of what we call civilization, you would be arriving at the other end right now, at this moment, in this year. That is how long the Orion Arm is. And if you were traveling not at the speed of light, but at the speed of our fastest actual spacecraft, crossing the arm would take on the order of 16 million years. 16 million years ago, the evolutionary lineage that would eventually produce human beings was still tens of millions of years from existing. The earliest hominid ancestors were millions of years in the future. The entire evolutionary journey from the common ancestor of apes and humans to the person reading these words took less time than it would take our best spacecraft to cross the arm we live in. The width is equally resistant to comfortable comprehension. At roughly 3,500 light-years across, the Orion Arm spans a distance that light alone requires 35 centuries to traverse. That is the width of the short dimension, the narrow way across, 35 centuries at the speed of light. In human terms, 3,500 years spans from the height of the New Kingdom in ancient Egypt to the present day, from the era of Ramesses the Great, who ruled a civilization already thousands of years old, to this exact moment in history. That is approximately how long light takes to cross the width of the structure we inhabit. Now, let us return to those diagrams. A standard printed illustration of the Milky Way, the kind found in textbooks and projected on planetarium domes, typically renders the galaxy at a width of about 30 centimeters. On that scale, the Orion Arm occupies roughly 3 centimeters of length and about 1 centimeter of width, 3 centimeters. The width of 2 fingernails placed side by side. That is what 10,000 years of light travel time looks like after compression. That 1 centimeter of width, which your eye registers and dismisses as a thin sliver, contains 35 centuries of light travel. Every fraction of a millimeter in that illustration corresponds to hundreds of light years of actual space. When your brain sees the Orion Arm on those diagrams and classifies it as small, it is processing 3 centimeters of ink. It is comparing 3 centimeters to the 20 or 25 centimeters occupied by the major arms and drawing the obvious visual conclusion. But that conclusion is catastrophically wrong, not because the diagram is made dishonestly, but because the act of representing galactic distances on a human-sized surface inevitably produces an image that misleads the visual system. There is no solution to this problem. You cannot draw the Orion Arm at true scale on any medium you can hold in your hands and still have it be useful. The compression is not a choice, it is a mathematical necessity. The consequence is that every person who has ever glanced at a galaxy diagram has been systematically taught to underestimate the scale of every feature depicted, not just the Orion Arm, everything. The major arms, which look impressively large on the page, are themselves grotesquely understated by the compression. The galactic center, which appears as a compact glowing bulge, is a region spanning 10,000 light-years across, comparable in extent to the entire Orion Arm. The distances between the arms, which look like modest gaps on the diagram, are themselves thousands of light-years of essentially empty space. But the Orion Arm suffers most from this effect, because it is already the smaller feature. The major arms at least occupy enough centimeters on the diagram to suggest magnitude. The Orion Arm, compressed into its 3-centimeter sliver, looks genuinely minor. And so the misimpression is deepest here, in the one place we actually live. Let us talk about what is actually inside the Orion Arm, because a structure 10,000 light-years long does not contain empty space and a few scattered stars. It contains billions of stars. It contains some of the most spectacular and celebrated objects in the entire observable sky. It contains stellar nurseries, dying stellar giants, the remnants of ancient explosions, clusters of young stars, and planetary systems numbering in the billions. The contents of the Orion Arm are not modest. They are extraordinary. Begin with the Orion Nebula. If there is one image that has appeared on more astronomy posters, more textbook covers, more desktop wallpapers than any other, it is probably this one. A vast glowing cloud of gas, illuminated from within by the fierce radiation of newborn stars. Its structure, a complex tapestry of violet and rose and amber, carved into arcs and columns and filaments by the stellar winds pouring off the young suns embedded inside it. The Orion Nebula sits approximately 1,340 light-years from Earth, comfortably inside the Orion Arm. The nebula itself spans roughly 24 light-years across, which means that light, crossing it from one side to the other, takes 24 years to make the journey. Inside that cloud, at this very moment, molecular clouds of hydrogen gas are collapsing under their own gravity. As they contract, they heat. As they heat, the pressure builds. Eventually, in some of these collapsing pockets of gas, temperatures reach the threshold at which hydrogen nuclei begin fusing into helium. A star ignites. This process is not metaphorical. It is not a slow, geological event. On cosmic timescales, it is rapid, and it is ongoing right now inside the Orion Nebula, 1,340 light-years away. Many of the young stars already born there are surrounded by rotating disks of gas and dust, the raw material from which planets will eventually form. Future solar systems are under construction inside a cloud that sits in our own arm of the galaxy. The Cygnus star-forming complex is another powerhouse of stellar birth within the Orion Arm. Located roughly 4,000 to 5,000 light-years from Earth in the direction of the constellation Cygnus, this enormous region contains multiple giant molecular clouds, numerous stellar nurseries, and some of the most massive and luminous stars known in our section of the galaxy. Within this complex lies the Cygnus OB2 Association, a grouping of thousands of young stars, including some of the most spectacularly bright stellar objects in the Milky Way. Individual stars radiating energy at rates hundreds of thousands of times greater than the Sun. These stars burn so intensely and so wastefully that their entire lives will span only a few million years before they exhaust their fuel and detonate. They are burning their inheritance in a geological eye blink, and they are doing it inside the Orion Arm. Betelgeuse needs little introduction. It is the bright reddish star marking the left shoulder of the constellation Orion, one of the most recognized points of light in the human night sky, across countless cultures and across thousands of years of human history. Betelgeuse sits somewhere between roughly 500 and 700 light-years from Earth, a range reflecting the genuine difficulty of measuring the distance to a star that is actively pulsating, expanding and contracting, changing its size and brightness over cycles that complicate the measurement. It is a red supergiant, a star that has exhausted the hydrogen fuel in its core and expanded to monstrous dimensions. If Betelgeuse were placed at the center of our solar system where the Sun currently sits, its outer atmosphere would engulf the orbit of Mars and likely reach deep into the asteroid belt, possibly extending as far as the orbit of Jupiter. Betelgeuse is dying. The exact timeline is uncertain. It could detonate as a supernova tomorrow, or the process could take another 100,000 years. Stellar physics does not operate on schedules convenient for human observation. But when it goes, the explosion will be visible from Earth in full daylight. It will outshine the full moon. For weeks, perhaps months, there will be a second sun in the sky, gradually fading as the expanding shell of ejected material cools and disperses. And this event, whenever it occurs, will be happening inside the Orion Arm, one of our neighbors, ending its existence in the most violent manner the universe permits for a single star. The Crab Nebula, is another landmark within the arm. In the year 1054, astronomers in China recorded the appearance of a new star in the sky, so bright it could be seen during daylight hours for nearly 3 weeks. They recorded it with the careful precision that characterized their astronomical tradition. What they witnessed was a star approximately 6,500 light-years away, reaching the end of its life and releasing the energy of billions of suns in a matter of seconds. Today, nearly 1,000 years after those observers first noticed the brightening, the remnant of that explosion is an expanding cloud of superheated gas roughly 11 light-years across, still pushing outward at enormous velocity. At its center sits a pulsar, the collapsed remnant of the original star's core, now a sphere roughly 20 kilometers across, but containing more mass than the Sun, spinning 30 times per second and sweeping beams of radiation through space like a lighthouse in the dark. The Crab Nebula is one of the most thoroughly studied objects in all of astronomy, and it resides inside the Orion Arm. The Veil Nebula is the shattered remains of a star that exploded roughly 11,000 years ago, at a distance of approximately 800 light-years. When that star detonated, it would have burned in the Earth's sky with a brilliance that the humans of that era, living at the end of the last ice age, would have found both magnificent and deeply unsettling. No written account exists because writing would not be invented for another 6,000 years. Today, the remnant is a vast, delicate lacework of glowing filaments stretched across roughly 100 light-years of space, the shockwave of that ancient explosion still expanding outward, still plowing through the surrounding interstellar gas. The Gum Nebula is among the largest emission nebulae in the sky, as seen from Earth, spanning approximately 36 degrees of the celestial sphere. To appreciate that figure, consider that the full moon covers about half a degree of sky. The Gum Nebula covers an area equivalent to roughly 70 full moons placed side by side. It lies about 1,500 light-years away and extends across roughly 1,000 light-years of actual space. A single object inside the Orion Arm that is itself 1,000 light-years in extent. One object, 1,000 light-years, and it is a relatively obscure item compared to the Orion Nebula or Betelgeuse. These named objects, the celebrated landmarks, the objects given entries in catalogues and featured in textbooks, represent a vanishing fraction of what the Orion Arm actually contains. For every nebula with a name, there are thousands without one. For every open cluster catalogued by astronomers, there are others in less studied directions that have never been systematically examined. And behind all of it, constituting the overwhelming majority of the Arm's contents, are the stars themselves. Within roughly 400 light-years of the Sun, a volume representing a tiny fraction of the Orion Arm's total extent, astronomers have catalogued tens of thousands of individual stellar systems. The European Space Agency's Gaia spacecraft, designed specifically to map stellar positions and motions with extraordinary precision, has now measured over 1 billion stars across the Milky Way. A substantial fraction of those billion measured stars belong to the Orion Arm. The arm is not sparse. It is populated with the full diversity of stellar life. Young blue giants blazing through their brief existence, middle-aged yellow dwarfs burning steadily for billions of years, ancient red giants that have expanded to swallow their inner planets, white dwarfs sitting cold and dense in the dark, and the dim red dwarfs that make up the majority of all stars by number, burning so slowly and so frugally that some of them will still be glowing in the unimaginably distant future when the universe is 10 times its current age. Within 50 light-years of the Sun, a sphere so small relative to the Orion Arm that it would be invisible on any diagram, there are approximately 2,000 known stars. 2,000 suns within 50 light-years. The Orion Arm is 10,000 light-years long. The volume of the arm exceeds the volume of that 50 light-year sphere by a factor so large that attempting to write it as a ratio would produce a number with more digits than there are seconds in a human lifetime. The arm is estimated to contain somewhere in the range of several billion individual stars distributed across its length and width and modest vertical extent within the galactic disk. Several billion stars, each one a nuclear furnace, each one a source of energy and light, and, in many cases, the gravitational anchor for a family of planets. And the question of planets, of how many worlds exist inside the Orion Arm, is one we can now begin to answer with real data, rather than speculation, thanks to a spacecraft that fundamentally changed what we know about the universe. In 2009, NASA launched a spacecraft called Kepler into an orbit trailing the Earth around the Sun. Its mission was deceptively simple in conception and staggeringly ambitious in execution. Point a telescope at a fixed patch of sky containing roughly 150,000 stars. Stare at those stars continuously for years without looking away. Record the brightness of every one of them, repeatedly, with extraordinary precision, and look for something specific, a tiny, periodic dimming, the almost imperceptible shadow cast when a planet passes across the face of its host star, blocking a fraction of that star's light for a matter of hours before moving on. This technique is called the transit method, and before Kepler demonstrated its power at scale, the honest answer to the question of how common planets are in the galaxy was that we genuinely did not know. We had discovered planets around other stars, yes. The first confirmed detection of a planet orbiting a sun-like star came in 1995 when Michel Mayor and Didier Queloz, two astronomers working at the Haute-Provence Observatory in France, identified a Jupiter-sized world orbiting the star 51 Pegasi in a shockingly tight orbit, completing one full circuit every 4 Earth days. That discovery, which would eventually earn Mayor and Queloz the Nobel Prize in Physics, cracked open a door. But it did not tell us whether planetary systems were common or rare. It told us only that they existed. Kepler answered the question of frequency. And the answer it returned transformed our picture of the galaxy entirely. Planets are not rare. Planets are not exceptional. Planets are the default condition of stars. The data gathered by Kepler over its 9 years of operation, before its fuel finally ran out in 2018, established beyond reasonable scientific doubt that on average, every star in the Milky Way hosts at least one planet. Not some stars, not most stars. Every star, on average. Many stars host multiple planets. Some harbor entire architectural systems, 5 or 6 or 7 worlds arranged in orbits ranging from scorchingly close to the star to distant and cold at the outer edges of the system. Rocky planets, the kind with solid surfaces and the potential for liquid water and the geological complexity that might support life, turned out to be substantially more abundant than anyone had predicted before Kepler began its observations. The mission that followed Kepler, a spacecraft called TESS, the Transiting Exoplanet Survey satellite, launched in 2018 and extended the survey to stars much closer to Earth, covering a far larger fraction of the sky. TESS has continued adding to the catalogue of known worlds, consistently confirming and extending what Kepler established. Planets are everywhere. They are not the exotic exception. They are the ordinary, unremarkable consequence of the star-forming process. When gas and dust collapse to form a star, the leftover material almost invariably organizes itself into a disk, and that disk almost invariably produces planets. It is not a special occurrence. It is simply what happens. Now apply those numbers to the Orion Arm. If the arm contains several billion stars, and if the average star hosts at least one planet, then the Orion Arm contains at least several billion planets. But the average from Kepler's data sits closer to 1.5 to 2 planets per star, once you account for planets that do not transit their host stars from our viewing angle and are therefore invisible to the transit method. That pushes the total number of worlds in the Orion Arm toward 10 billion, perhaps higher. 10 billion planets. Inside those 3 centimeters on a textbook diagram, the diversity of those worlds spans a range that our solar system alone hints at only partially. Gas giants like Jupiter, immense spheres of swirling hydrogen and helium, where the concept of a surface has no meaning, where storms larger than Earth persist for centuries. Ice giants wrapped in mantles of frozen water and methane, dimly lit and perpetually cold. Super-Earths, a class of planet with no analogue in our own solar system. Rocky worlds larger than Earth but smaller than Neptune, some of them potentially harboring deep global oceans beneath crushing atmospheres. And then the rocky terrestrial worlds. The solid surface planets with masses comparable to Earth, where geology can operate, where atmospheres can be retained, where the conditions for liquid water on the surface are at least conceivable. Of all those categories, the rocky terrestrial worlds, orbiting within their star's habitable zone, attract the most attention for obvious reasons. The habitable zone is simply the range of orbital distances at which a planet receives enough stellar energy to maintain liquid water on its surface, neither so close that the water boils away, nor so far that it freezes permanently. It is not a guarantee of life. It is a prerequisite, based on our one confirmed example of a life-bearing world, for the kind of surface chemistry that life as we understand it requires. Kepler's data suggests that roughly 1 in 5 Sun-like stars may host a rocky planet within its habitable zone. For red dwarf stars, the most numerous stellar type in the galaxy, the fraction may be even higher, though habitable zones around red dwarfs come with their own complications, including intense stellar flares and the tendency for planets to become tidally locked, always showing the same face to their star. Even applying conservative estimates, the number of rocky worlds within habitable zones across the Orion Arm reaches into the hundreds of millions. Hundreds of millions of worlds where, at minimum, the basic physical conditions for liquid water could in principle exist. Every single one of them unknown to us by name, every single one of them unexplored. Every single one of them sitting in the darkness between the stars inside the one feature of the Milky Way that our diagrams have spent decades convincing us to regard as a minor footnote. There is a particular kind of stillness that settles over a person when these numbers are genuinely absorbed rather than merely acknowledged. Not the glib acknowledgement of something intellectually interesting, the kind that lasts for a moment and then dissolves back into the ordinary concerns of daily life, but the actual, sustained recognition that the arm you inhabit, this one structure you have lived inside for your entire existence without ever being aware of its boundaries, contains more worlds than any civilization could visit in any span of time worth contemplating. Hundreds of millions of potentially habitable worlds, and we have examined, in any meaningful sense, precisely one of them. And on that one world, after 4 billion years of biological evolution, something emerged that could look outward and begin to count the others. That is where we are. That is what we are. We are the part of the Orion Arm that learned to ask how many worlds the Orion Arm contains, and the answer, delivered by careful instruments and patient analysis, is more than we will ever be able to visit. But the Orion Arm does not exist in isolation. It sits between two of the galaxy's major spiral arms, and understanding how those arms compare to the Orion Arm in scale and activity is what completes the picture of why the diagrams mislead us so effectively. The Perseus Arm lies outward from our position, between us and the galaxy's outer edge. It is one of the two primary arms in most structural models of the Milky Way, sweeping in a long arc around a significant portion of the galaxy. Its estimated length varies depending on where you define its boundaries, but most studies place it at somewhere between 30,000 and 40,000 light-years, and some analyses suggest it extends even further. The Perseus Arm is rich with star-forming regions and populated by enormous concentrations of massive young stars. Its molecular clouds are among the most active stellar nurseries in our region of the galaxy. If you could hover above the Milky Way and look down, the Perseus Arm would be one of the most visually dominant features you would see. A bright, luminous arc tracing a grand curve through the galactic disk. The Perseus Arm is 3 to 4 times the length of the Orion Arm. Let that comparison register properly. Not that the Orion Arm is small, but that the Perseus Arm is 3 to 4 times the length of something that is already 10,000 light-years long. The Perseus Arm is 30 to 40,000 light-years. If crossing the Orion Arm at the speed of light takes 10,000 years, crossing the Perseus Arm at the speed of light takes 30 to 40,000 years. 30 to 40 millennia of continuous travel at the fastest speed the universe permits. Now, consider the Sagittarius Carina Arm on the other side of us, between our position and the galactic center. This arm is also a major feature, comparable in length to the Perseus Arm, estimated at roughly 30,000 light-years or more. When you look toward the constellation Sagittarius on a summer night, You are looking through this arm toward the galactic core, the dense luminous band of the Milky Way visible in that direction. The concentrated glow that has caught human attention since before recorded history is largely the combined light of stars in the Sagittarius Arm and the denser regions beyond it. The Sagittarius-Carina Arm contains objects that have become iconic in the history of astronomy. The Eagle Nebula, which became famous when the Hubble Space Telescope captured an image of towering columns of gas and dust inside it, columns light-years tall being sculpted by radiation from nearby young stars, while new stars condense within their shadowed interiors, sits roughly 7,000 light-years from Earth inside the Sagittarius Arm. Those columns, which became perhaps the most widely reproduced astronomical image of the 20th century, are structures inside a different arm of the galaxy than the one we inhabit, 7,000 light-years away. The Omega Nebula, another massive stellar nursery sometimes called the Swan Nebula, lies at a similar distance within the same arm. And then there is the Scutum Centaurus Arm. By many measures, this is the most massive and prominent arm in the entire Milky Way. It originates from one end of the galaxy's central bar and sweeps outward in an enormous arc that may extend for 60,000 light-years or more, depending on where its outer boundary is traced. Some analyses identify it as the single dominant arm of the galaxy, containing the highest total density of stars and interstellar gas of any spiral feature. It passes through some of the most prolific star-forming regions in the Milky Way, particularly in the zones near the galactic bar, where gas is gravitationally funneled inward and compressed into conditions of extreme density. Inside the Scutum Centaurus Arm are stellar clusters, so massive and so luminous that they have no counterpart anywhere in our local region of the galaxy, assemblages of thousands of hot, massive stars blazing with a collective brilliance that would be visible across tens of thousands of light-years. Now, hold all of this alongside the Orion Arm. The Orion Arm, at 10,000 light-years long, sits next to the Perseus Arm at 30 to 40,000 light-years. It sits next to the Sagittarius-Carina Arm at a similar length. It sits next to the Scutum Centaurus Arm, which may be 6 times its length. These are the structures flanking our home on either side, and on any diagram they dwarf it. But there is a comparison that clarifies what is really happening here. Consider a river and an ocean. Nobody needs to be told that the ocean is vastly larger than any river. The difference in scale is enormous and obvious, but nobody looks at the Amazon River and concludes that it is insignificant. Nobody stands at the bank of the Congo and thinks, this is a trivial feature of the landscape, barely worth mentioning, because the Atlantic Ocean exists. The river is a colossal feature in its own right. It contains an immense volume of water. It sustains an extraordinary diversity of life. It has shaped entire continents over geological time. It is one of the most powerful and consequential physical features on Earth. It is simply smaller than the ocean, and being smaller than the ocean does not diminish what it is. The Orion Arm is the river in this comparison. The major spiral arms are the ocean. The Orion Arm is genuinely shorter, less massive, less active in star formation, less visually dominant in the galactic structure. Those are facts. But they are facts about its relative position in a hierarchy of structures that are all, without exception, incomprehensibly vast. Being smaller than the Perseus Arm does not make the Orion Arm small. It makes it smaller than something that is itself almost inconceivably large. This distinction between being small and being merely smaller than something enormous is the central insight that galaxy diagrams systematically prevent people from reaching. Because on a diagram, small-looking and small are indistinguishable. Your visual system has no way to tell the difference between something that is genuinely minor and something that merely looks minor because everything on the page has been compressed by a factor of millions. The diagram shows you a proportional relationship, and your brain constructs a judgment of absolute scale from it. But absolute scale cannot be inferred from proportional diagrams when the compression is this extreme. The inference fails, and we have been making that failed inference every time we have looked at a picture of the Milky Way. Now let us bring in one more comparison point, the galactic center itself. Sagittarius A star, the supermassive black hole, anchoring the Milky Way's gravitational structure, has a mass approximately 4 million times that of the Sun. Around it, in the innermost regions of the galaxy, stars move at speeds that would be extraordinary by any standard we are accustomed to. A star designated S2, one of a cluster of stars orbiting closely around the black hole, completes a full orbit every 16 years and reaches speeds of roughly 3% of the speed of light at its closest approach. That is approximately 9,000 kilometers per second. Our Sun, at 230 kilometers per second, is moving nearly 40 times more slowly. The galactic center is a place where the physics operates at scales of violence and speed that have no parallel in our quiet corner of the arm. The galactic bulge surrounding the central bar spans roughly 10,000 light-years across its widest extent. 10,000 light-years. That is comparable to the entire length of the Orion Arm. The central concentration of the galaxy, the dense knot of ancient stars packed around the bar and the black hole at the heart of the Milky Way, occupies a volume of space roughly equivalent in one dimension to the full length of the structure we call home. And the bulge is just one component of the galactic center region. The bar itself extends for roughly 27,000 light-years, nearly 3 times the Orion Arm's length. And the bar is in turn just one component of the overall structure of the inner galaxy. When you place the Orion Arm next to the galactic center structures, it looks like an extension off to one side, a long spur reaching out from the more compact but enormously dense inner regions of the galaxy. And in a sense, that is exactly what it is. We are out here on the Arm, 26,000 light-years from the dense beating heart of the Milky Way, in a region of relative quiet and stability, orbiting patiently while the inner galaxy operates at a pace and intensity that would be inimical to everything we depend on. There is one more dimension of comparison worth making, and it involves the galaxy's overall geometry. The Milky Way's disk, at the distance of the Sun from the center, has a circumference of roughly 160,000 light-years measured along the approximate circle of the Sun's orbit. The Orion Arm, at 10,000 light-years in length, covers roughly 6% of that circumference. 6%. That sounds modest. It sounds like a thin sliver of the pie. But 6% of 160,000 light-years is 10,000 light-years. And we have already established what 10,000 light-years means in terms of travel time and physical distance. 6% of something galaxy scale is still a structure of staggering proportions. The fraction is small, the thing it represents is enormous. This is the perceptual trap that awaits anyone who tries to understand their place in the galaxy by reasoning from percentages and proportions rather than from absolute numbers. Percentages strip away the context of scale. They tell you how something relates to a reference point without telling you how large that reference point is. When someone says the Orion Arm occupies 6% of the galaxy's circumference at our orbital distance, your brain hears 6% and feels modest, small, negligible. But the galaxy's circumference at our orbital distance is 160,000 light-years. 6% of that is 10,000 light-years. And 10,000 light-years is not small by any standard your direct experience has ever equipped you to apply. Every percentage, every fraction, every proportional description of the Orion Arm relative to the galaxy suffers from this problem. The numbers are accurate, the fractions are correctly calculated, but the emotional impression they create, the sense of smallness and insignificance they produce in the listener, is wrong. It is a category error, a confusion between relative and absolute scale. The Orion Arm is small relative to the Milky Way in the same sense that a river is small relative to an ocean. The relationship is real, but the absolute scale of the smaller thing remains staggering regardless of the comparison. The Orion Arm is real. It is enormous. It contains billions of stars and billions of worlds and stretches for 10,000 years of light travel from end to end. The major arms that flank it are larger. The galaxy that contains it all is larger still. But none of that changes what the Orion Arm actually is. None of that makes its 10,000 light-years any shorter. None of that reduces the number of stars inside it by a single sun. The diagrams have shown you a proportion. They have never shown you the scale. And the scale is what matters. For most of human history, the question of what the Milky Way actually looks like was not merely unanswered. It was not even properly formulated. People looked up at the pale band of light stretching across the night sky and wondered what it was. But the tools needed to begin answering that question at any meaningful depth did not exist until the 20th century. The understanding that the Milky Way is a galaxy, a vast rotating disk of hundreds of billions of stars, that our Sun is one ordinary member of that disk located far from its center, and that other galaxies exist beyond our own, independent island universes separated from us by millions of light years, all of this was established only within the last 100 years. In the full span of human existence, our knowledge of the structure we inhabit is extraordinarily recent, and mapping that structure in detail has proven to be one of the most technically demanding challenges in the history of science. Not because the tools available to astronomers are inadequate in any ordinary sense. The observatories and telescopes and space-based instruments that humanity has built represent marvels of engineering and ingenuity. The difficulty is more fundamental than that. It is the problem of perspective. You are inside the thing you are trying to map, and being inside it prevents you from ever seeing the whole. Consider what mapping the Milky Way's spiral structure actually requires. You need to know the three-dimensional positions of stars and gas clouds distributed across distances ranging from a few light years to tens of thousands of light years. You need to know which features form coherent structures and which are chance alignments of unrelated objects at different distances along the same line of sight. And you need to make all of these measurements without ever being able to step outside the galaxy and look at it whole. Every observation you make is a view from within, looking outward through layers of intervening stars and gas and dust that absorb and scatter light, obscuring the more distant regions and making distance estimation a complex, error-prone enterprise. For much of the 20th century, the primary tool for tracing the Milky Way's spiral structure was radio astronomy, specifically the observation of hydrogen gas at a wavelength of approximately 21 centimeters. Hydrogen is the most abundant element in the universe, and it fills the spaces between stars in the form of a thin, diffuse medium permeating the galactic disk. Under certain conditions, the electrons in hydrogen atoms undergo a subtle transition that releases a photon at precisely 21 centimeters wavelength. Radio waves at this frequency pass through the dust clouds that block visible light, meaning that radio telescopes can detect hydrogen gas even in distant regions of the galaxy that are completely obscured at optical wavelengths. By observing this 21 centimeter emission from hydrogen clouds across the sky and measuring the Doppler shift of the signal, the way the frequency changes depending on whether the emitting gas is moving toward or away from us, astronomers could estimate the velocities of hydrogen clouds throughout the galaxy. Since gas at different distances from the galactic center orbits at different speeds, a measured velocity could in principle be converted into a distance estimate. This technique, known as the kinematic distance method, was the primary means by which astronomers traced the spiral structure of the Milky Way for decades. It produced a picture, a rough, somewhat blurry picture, but a picture nonetheless. The major spiral arms emerged from these observations as regions of elevated hydrogen density, tracing broad arcs around the galactic center. The Orion Arm appeared as a feature in our immediate neighborhood, a concentration of gas and young stars in the region surrounding the Sun. But the kinematic distance method came with significant limitations that consistently blurred and distorted the picture it produced. The method relies on a model of how the galaxy rotates. It assumes that all gas clouds orbit the galactic center in smooth, circular orbits, so that a measured velocity can be unambiguously converted into a distance. But real gas clouds do not orbit in perfect circles. They have local motions driven by the gravity of nearby star clusters, by the pressure of expanding supernova remnants, by the turbulence of star-forming regions. These local velocities add to or subtract from the orbital velocity, introducing errors into the distance estimates that can be substantial. A gas cloud that happens to be moving slightly faster than the average orbital velocity for its distance will appear, to the kinematic method, to be located somewhere it is not, near the galactic center, the method breaks down almost completely, because in that region the orbital velocities become ambiguous and small errors in velocity measurement translate into enormous errors in distance. And near the Sun's own orbital distance from the center, there is a similar problem of ambiguity. The result is that the kinematic distance method, while powerful, produces maps with large uncertainties, maps where the positions of features are smeared across ranges of possible distances rather than pinpointed with precision. This imprecision had real consequences for our understanding of the Orion Arm specifically. Because the Orion Arm is right where we are, it is in precisely the region where the kinematic method works least reliably. There is a deep irony in this. The part of the galaxy closest to us, the part we most urgently want to understand because we live in it, is the part that is hardest to map using the tools that work well for distant features. We are too close to our own neighborhood to see it clearly with radio velocity measurements. Optical observations of bright young stars and ionized hydrogen regions provided a complementary approach. Hot, massive stars and the glowing nebulae they illuminate are concentrated in spiral arms because those arms are where star formation occurs. By cataloging the positions and estimated distances of these objects, astronomers could attempt to trace the arm structure in 3 dimensions, but distance estimates for individual stars carried their own uncertainties. The most common technique was spectroscopic parallax, which involves comparing a star's observed brightness to its expected brightness based on its spectral characteristics, then calculating how far away it must be to appear as bright as it does. This method is reliable in a statistical sense but carries individual uncertainties that can exceed 30%. 30% uncertainty on a distance of several thousand light-years means your measurement could be off by 1,000 light-years or more. When you are trying to trace the boundaries and extent of a feature that is itself only 3,500 light-years wide, a 1,000 light-year error on individual measurements makes it extremely difficult to determine whether a given star is inside the arm, outside it, or somewhere near its edge. The consequence was that the classification and dimensions of the Orion Arm remained genuinely uncertain for decades. Some analyses concluded it was a short spur, a minor connector between the Sagittarius Carina and Perseus arms, perhaps 3,000 to 4,000 light-years in length. Others suggested it was longer and more substantial. Some researchers argued it might qualify as a genuine arm segment rather than a spur, while others maintained the spur classification on the grounds that it lacked the length and mass of the major features. The data, gathered with the best instruments available, simply could not resolve the question to everyone's satisfaction. Then, something changed. In December of 2013, the European Space Agency launched a spacecraft called Gaia from the Kourou spaceport in French Guiana aboard a Soyuz STB rocket. Gaia was designed to do something that had never been done before at anything approaching its scale. It would measure the positions and motions of stars across the Milky Way with a precision so extreme that it would essentially create an entirely new foundation for our understanding of galactic structure. The technique Gaia uses is called astrometric parallax, and its principle is ancient. As Earth orbits the Sun over the course of a year, nearby stars appear to shift slightly against the background of more distant stars because we are viewing them from slightly different angles at different points in our orbit. This apparent shift, called parallax, can be measured and converted directly into a distance. The closer the star, the larger the parallax shift. The farther the star, the smaller and harder to detect the shift becomes. Ground-based telescopes had been using this method for centuries, but atmospheric turbulence and other limitations restricted reliable parallax measurements to stars within a few hundred light-years. Gaia operates in space, above the atmosphere, measuring stellar positions with an angular precision of roughly 10 microarcseconds. For the brightest stars in its catalogue, 10 microarcseconds is an almost incomprehensible degree of precision. It corresponds to the angle subtended by a €1 coin viewed from a distance of roughly 100,000 kilometers. At that precision, Gaia can measure reliable parallax distances for stars thousands of light-years away, a capability that was simply not achievable with any previous instrument. By 2022, Gaia had released data on nearly 2 billion stars, providing not just distances but also proper motions, the gradual drift of stars across the sky over time as they pursue their orbits through the galaxy. This combination of precise distance and motion information transformed the study of Milky Way structure from an exercise in uncertain inference to something approaching direct measurement. For the first time, astronomers could plot the three-dimensional positions of millions of individual stars across a substantial fraction of the galactic disk and ask, with genuine precision, where the spiral arms actually are. The results were illuminating in ways that went beyond simply confirming what the kinematic maps had suggested. Studies using Gaia data found that the Orion Arm is more substantial and more coherent than older analyses had indicated. By tracing the positions of young stars, open star clusters, and a class of variable stars called classical Cepheids, which pulsate with a period directly related to their intrinsic luminosity and therefore serve as extremely reliable distance markers, researchers found that the Orion Arm extends significantly farther than the traditional estimates suggested. Cepheid variable stars deserve a moment of attention here, because their role in galactic mapping is fundamental. These are stars that expand and contract in regular cycles, brightening and dimming with a period that ranges from days to months. In 1908, an astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory, under conditions that would today be recognized as deeply inequitable, was assigned the painstaking task of cataloging variable stars in photographs of the Small Magellanic Cloud, one of the small galaxies orbiting. She identified nearly 2,000 variable stars and noticed something extraordinary. The brighter ones had longer periods. There was a clean, quantitative relationship between how long a Cepheid took to complete one pulsation cycle and how intrinsically luminous it was. This period luminosity relationship meant that by simply measuring how long a Cepheid takes to pulse, you can calculate how bright it actually is. Compare that intrinsic brightness to how bright it appears from Earth, and you have a direct measurement of its distance. Leavitt's discovery effectively gave astronomers a standard candle, a reliable method for measuring cosmic distances across ranges that parallax could not reach. It was this tool that Edwin Hubble used in 1923 to measure the distance to the Andromeda Galaxy and establish that it lay far beyond the boundaries of the Milky Way, confirming that the universe contains galaxies beyond our own. Now Gaia has measured precise distances and motions for enormous numbers of Cepheids distributed across the galactic disk, providing the most accurate three-dimensional map of spiral arm structure the Milky Way has ever had. And in that map, the Orion Arm shows up as a coherent, well-defined, elongated structure with a pitch angle, the angle at which the arm inclines relative to the galaxy's circular symmetry, of roughly 10 to 12 degrees. That pitch angle matters for a specific reason. The major spiral arms of the Milky Way have pitch angles in the same range, roughly 10 to 15 degrees. A genuine interarm spur, a random clump of material between two major arms rather than a real structural feature, would not necessarily share the pitch angle of the major arms. The fact that the Orion Arm's pitch angle falls comfortably within the range of the major arms suggests that it is not a random bridge or connector. It is a real spiral feature, organized by the same large-scale density wave dynamics that produce the major arms, simply at a smaller scale. Several research teams analyzing Gaia data have now traced the Orion Arm to lengths significantly exceeding the traditional 10,000 light-year estimate. Some analyses suggest it may extend to 15,000 light-years. Others trace it even further, potentially to 20,000 light-years or more, depending on which stellar populations are used as tracers and where the arm's boundaries are defined. If the longer estimates prove correct, the Orion Arm may be comparable in length to some of the shorter major arm segments in other spiral galaxies, and its classification as a mere spur would require reconsideration. Measurements of a class of radio sources called masers, natural sources of intense microwave radiation found in star-forming regions, have provided yet another line of supporting evidence. Masers emit their radiation in narrow, focused beams and can be observed with radio telescopes at great distances. Using a technique called very long baseline interferometry, which combines signals from radio telescopes separated by thousands of kilometers or even across different continents, astronomers can achieve angular resolutions sharp enough to measure the parallax distances of masers directly, even at distances of thousands of light years. This technique has been applied to masers distributed along the Orion Arm and has produced distance measurements consistent with a coherent, extended structure rather than a random assemblage of unrelated star-forming regions. The picture that emerges from all of this new data is not a minor revision of the old picture. It is a substantive upgrade of our understanding of the Orion Arm's nature and significance. The arm is longer than we thought. It is more coherent in its structure than older analyses implied. Its pitch angle aligns with the major arms. Its stellar populations and star-forming regions are distributed in a pattern consistent with a genuine spiral feature, rather than a transient or accidental grouping. The terminology is shifting in the scientific literature to reflect this. Many researchers now prefer the term local arm over Orion Spur or Orion Cygnus Arm, with the word arm carrying a structural weight that Spur has never quite implied. None of this means the Orion Arm has been reclassified as equal to the Perseus or Scutum Centaurus arms. It has not. Even at 20,000 light-years, if that length holds up under further analysis, it remains shorter than the major arms. Its star formation rate remains lower. Its total stellar mass remains smaller. It is a secondary feature of the Milky Way's spiral structure, and that is unlikely to change, no matter how much more data is gathered. But here is what this evolving picture actually means. Every time our measurements improve, the Orion Arm gets larger. The kinematic maps of the mid-20th century suggested a short spur of a few thousand light-years. Better optical surveys push the estimate toward 10,000. Gaia is pushing it further still, toward 15 or 20,000. The trend is consistent and clear. Each generation of instruments, each improvement in measurement precision, reveals the Orion Arm to be more extensive and more structured than the previous generation of instruments could see. This is a pattern that appears repeatedly in the history of astronomy. The universe, examined more closely, is always larger and more complex than it appeared from a distance. The solar system turned out to be vaster than early telescopes suggested. The Milky Way turned out to be vastly larger than 18th century astronomers estimated. The universe turned out to contain 2 trillion galaxies, rather than the hundreds of millions estimated before deep field imaging revealed the full extent of the cosmic web. In each case, the improvement of instruments revealed more than was previously visible, and more always meant larger, more complex, more extraordinary than what came before. The Orion Arm is following this pattern exactly. As our ability to measure it improves, it grows. Not because the arm itself is changing. It has been whatever size it is for billions of years. But because our instruments are finally becoming sensitive enough to see it properly, to trace its full extent rather than only the brightest and nearest portions of it, and to measure individual stellar distances with precision sufficient to distinguish the arm's coherent structure from the background scatter of stars in the interarm regions. What this means for the central argument of this entire exploration is straightforward. The Orion Arm has already been shown to be vastly larger than the diagrams suggest, and the latest evidence indicates it is larger even than the traditional measurements implied. The standard estimate of 10,000 light-years, which we have been using throughout this journey, may itself be an underestimate. The real arm may be half again as long, or twice as long, or longer still. Each new data release from Gaia tightens the measurements and pushes the boundaries further out. We are in the early stages of truly understanding the structure we inhabit. The forest is beginning to reveal its full extent, not because we have stepped outside it, but because we have finally built instruments sensitive enough to see the distant trees from within. And those distant trees, it turns out, are farther away than we thought. The forest is larger than the maps ever showed. Our position within the arm has not changed. The sun still sits roughly along the inner edge of the Orion Arm, 26,000 light-years from the galactic center, between the Sagittarius-Carina Arm inward and the Perseus Arm outward. We are still in the same quiet, stable, secondary feature of the Milky Way that sheltered the formation of our solar system 4.5 billion years ago. But the feature itself, our address in the galaxy, our neighborhood in the cosmos, is turning out to be a more significant piece of the galactic architecture than anyone realized when the first rough maps were drawn. The arm we live in is not a footnote. The instruments are finally telling us so, one precise stellar parallax at a time. We have been pulling back this entire time, zooming out, expanding the frame, placing the Orion Arm inside the galaxy and the galaxy inside the universe, watching each level of the hierarchy dwarf the one below it. But there is another direction to travel, and it is equally disorienting. Not outward, but inward. Not toward the grand sweep of galactic structure, but toward the immediate, the local, the region of space that surrounds the sun right now and constitutes our most intimate neighborhood in the cosmos. Because the Orion Arm is not merely a number on a page, it is not just a measurement of length and width to be compared against the major arms and found either impressive or modest, depending on your reference point. It is a physical place, a three-dimensional volume of space with its own internal structure, its own neighborhoods within neighborhoods, its own history of violence and creation, stretching back billions of years. And to understand what the Orion Arm truly contains, you need to begin not at its edges, but at its center, at the sun, at us. Start as close can be. Within roughly 15 light-years of the sun, astronomers have catalogued approximately 50 star systems. 50, a sphere 30 light-years across, centered on our solar system, containing 100 stellar objects. Some of them are single stars like the sun. Some are binary pairs, two stars locked in mutual orbit, circling each other over periods ranging from days to thousands of years. A few are triple systems, three stars in complex gravitational arrangements that in some cases have persisted stably for billions of years. You might recognize some of the names. Proxima Centauri, the closest star to the sun at 4.24 light-years, a dim red dwarf, so faint that despite being our nearest neighbor, it cannot be seen with the naked eye from Earth. Alpha Centauri A and B, the binary pair that Proxima orbits at a distance of roughly 4.37 light-years, the two brightest components of which are sun-like stars, whose combined light makes the system the third brightest point of light in the night sky, as seen from Earth. Barnard's star, a red dwarf about 6 light-years away that moves across the sky faster than any other known star relative to the sun, covering the apparent diameter of the full moon every 180 years due to its combination of proximity and high velocity. Sirius, the brightest star in the night sky, sitting at a distance of approximately 8.6 light-years, a star about twice the mass of the sun and 25 times more luminous, so bright from Earth that for centuries it was used as a calendar marker and a navigational reference by civilizations across the ancient world. These are our neighbors, the stars right next door, the closest objects in the galaxy to our own solar system. And even this tiny cluster of nearby stars, this intimate cosmic community, is already separated from us by distances that reduce every spacecraft humanity has ever launched to something approaching irrelevance. Voyager 1 is our most distant emissary. Launched in September of 1977, it has been traveling continuously away from Earth for nearly 50 years. It is the farthest human-made object in existence, and it has covered approximately 24 light-hours of distance from the Sun. Not 24 light-years, 24 light-hours, the distance light covers in one day. Proxima Centauri is 4.24 light-years away. 1 light-year is 8,760 light-hours. Proxima Centauri is therefore approximately 37,000 light-hours from the Sun. Voyager 1 has covered 24 of those 37,000 light-hours in nearly 50 years of continuous travel. If Voyager 1 were heading toward Proxima Centauri, which it is not, it would require approximately 73,000 years to arrive. 73,000 years. Agriculture was invented 10,000 years ago. The entirety of recorded human civilization fits inside a tenth of the time it would take our fastest departing spacecraft to reach the nearest star. We have been traveling outward for 50 years, and covered less than 1/1500th of the distance to our closest stellar neighbor. That is our immediate front yard, 15 light years, half 100 stars, and we cannot reach any of them. Now expand. Within 100 light years of the Sun, the known stellar population climbs to roughly 14,000 star systems, a sphere 200 light years across, containing 14,000 suns. This region encompasses many of the stars that have names in human cultural traditions, the bright familiar points of light that have guided travelers and inspired mythology and anchored the constellations recognized by cultures across the world for thousands of years. Vega lies about 25 light years away, a blue-white star, roughly twice the mass of the Sun, that rotates so rapidly it is visibly flattened at its poles, bulging at its equator like a spinning water balloon. Arcturus sits at about 37 light years, a red giant in the later stages of its life, one of the brightest stars in the night sky. Capella lies at approximately 43 light years, actually a system of 4 stars, 2 bright yellow giants orbiting each other every 104 days, accompanied by 2 dim red dwarfs at a much greater distance. Fomalhaut, about 25 light years away, is surrounded by a disk of debris that astronomers have studied carefully for evidence of planetary formation, and within that disk there appears to be at least one planet. Every one of these stars is inside that 100 light-year bubble. Every one of them is unreachably far from us with current technology. And that bubble, that sphere 200 light-years across containing 14,000 stellar systems, represents exactly 1% of the Orion Arm's length. 1%. We have expanded our view to include 14,000 stars across a volume it would take light 200 years to cross, and we have covered 1% of the arm we live in. The remaining 99% stretches away from us in every direction, containing billions of additional stars, thousands of additional light years, and a complexity and richness of structure that we have only barely begun to observe. Expand again. Within 500 light years, the stellar population climbs into the hundreds of thousands. The volume of this sphere is now enormous, spanning 1,000 light years from one side to the other. Within it, you find stars at every stage of the stellar life cycle. Newly ignited young stars still embedded in the gas clouds that gave birth to them, their radiation ionizing the surrounding hydrogen into glowing nebulae. Middle-aged stars like the Sun burning steadily through the long, calm middle portion of their lives. Red giants that have exhausted the hydrogen in their cores and expanded to monstrous dimensions as they transition toward the later stages of stellar evolution. White dwarfs, the dense crystallizing remnants of stars that completed their lives billions of years ago, now slowly cooling in the dark. Binary systems, triple systems, open clusters of young stars still drifting apart from the molecular cloud that formed them millions of years ago. Within 500 light years, there is already more variety, more complexity, more astronomical richness than any catalogue compiled by any civilization in any reasonable span of time could fully document. Every region of that sphere has its own character. Some neighborhoods are dense with young stars and active star formation. Others are quieter, populated mainly by older stars that formed in an earlier era of the galaxy's history. Some regions contain the remnants of stars that exploded thousands of years ago, their shock waves still expanding outward through the surrounding gas. 500 light years represents 5% of the Orion Arm's length. We have barely started, but before pushing further outward, there is something within roughly this scale, within about 1,000 light years of the Sun, that deserves particular attention. Because it reveals something important about the internal structure of the Orion Arm, the fact that even within a single spiral feature, the environment is not uniform. It is layered and textured, shaped by events that unfolded millions of years ago, organized into distinct neighborhoods, each with its own physical character and its own history. This structure is called the local bubble. The local bubble is a cavity in the interstellar medium, the diffuse gas and microscopic dust particles that fill the spaces between stars throughout the galactic disk. Under normal conditions, this interstellar medium has a characteristic density, thin by any laboratory standard but not negligible across the enormous distances of space. The local bubble is a region where that density is dramatically reduced. It is a pocket of extremely thin, extremely hot gas carved into the surrounding denser material of the Orion Arm. Its shape is irregular, more reminiscent of an elongated lumpy cavity than a geometric sphere, and it spans roughly 1,000 light-years across its longest dimension. The Sun is inside it. Our entire immediate stellar neighborhood, every star visible to the naked eye, every star system within a few hundred light-years of Earth, sits within this bubble of unusually thin interstellar gas. How did it form? The answer is both straightforward and humbling. Supernova explosions, specifically a series of them. Somewhere between 10 and 15 million years ago, a group of massive stars in our region of the Orion Arm reached the end of their brief, violent lives in rapid succession. These were not distant events. By galactic standards, they were close enough that their combined shock waves, the expanding shells of superheated gas and energy released by each successive explosion, swept through the surrounding interstellar medium with enough force to push the gas outward, compressing it into an expanding shell and leaving behind a hot, tenuous cavity where the gas had been. The Sun did not cause this. The Sun is a stable, middle-aged star that has been burning quietly for 4.5 billion years and will continue doing so for approximately another 5 billion. The Sun simply happened to drift into the region cleared by those ancient explosions. At some point in the past few million years, the Sun's orbit carried it into the interior of the cavity blown by those dead stars, and here it remains. We are floating inside a bubble created by stellar deaths that occurred before our most recent ancestors had fully diverged from other great apes. The local bubble has real physical consequences for the environment we inhabit. The thin hot gas filling the interior emits X-rays, a faint diffuse glow of high-energy radiation detectable by space-based X-ray observatories. The reduced density of interstellar gas inside the bubble affects how cosmic rays, high-energy particles streaming through the galaxy from distant supernova remnants and other energetic sources, propagate through our neighborhood. It affects the interstellar pressure environment experienced by the outer edges of the solar system, where the Sun's own outflowing solar wind meets the surrounding galactic medium. But perhaps the most striking discovery about the local bubble came relatively recently from studies using Gaia data and three-dimensional maps of nearby star-forming regions. In 2022, a research team led by astronomer Catherine Zucker published an analysis showing that essentially every active star-forming region within roughly 1,000 light-years of the Sun sits on the surface of the local bubble, not inside it, not randomly distributed around it, on its surface, along the compressed shell of denser gas that marks the bubble's boundary, where the material pushed outward by those ancient supernova accumulated and eventually became dense enough to begin collapsing under its own gravity. The explosions that cleared our local region of interstellar gas also created the conditions for new stars to form at the bubble's edges. The gas was pushed outward, compressed into a shell, and that shell became a star-forming region, death seeding creation. The Orion Nebula, that iconic stellar nursery 1,340 light-years from Earth, sits on the surface of the local bubble. The Perseus molecular cloud, another active star-forming region, sits on the surface of the local bubble. The Taurus molecular cloud, one of the closest star-forming regions to the Sun, sits on the surface of the local bubble. All of them triggered, or at least substantially influenced, by the shock waves of explosions that took place millions of years before any of them began forming stars. This is not a minor detail. This is the Orion Arm revealing its internal complexity. A single spiral feature of the Milky Way contains, within a region covering roughly 10% of its length, a nested structure of extraordinary richness. Ancient supernova carve cavities. Those cavities compress surrounding gas into shells. Those shells collapse to form new stellar nurseries. Those nurseries produce new generations of massive stars. Those massive stars eventually explode, potentially carving new cavities and beginning the cycle again. The arm is not a static collection of stars and gas. It is a dynamic, self-organizing system, recycling its material through generations of stellar birth and death, each cycle leaving its signature on the local environment in the form of bubbles and shells and triggered star-forming regions. And all of this is happening inside the one feature that galaxy diagrams draw as a thin, unremarkable sliver between two grander structures. Now push further outward. At a distance of 1,000 light-years, the sphere centered on the Sun has grown to 2,000 light-years across and encompasses millions of stars. Major astronomical landmarks begin to appear. The Orion Nebula, at 1,340 light-years, falls just within this volume. The Pleiades cluster, that beautiful group of young blue stars at about 440 light-years, is well inside it, its brightest members visible to the naked eye on winter nights, and recognized by cultures from ancient Greece to the Aboriginal peoples of Australia to the Maori of New Zealand. The Hyades cluster, at about 150 light-years, the nearest open cluster to the Sun, is deep within it. At this scale, the region of space begins to have its own geography. Stars are not uniformly distributed. They cluster in groups and associations. Gas and dust form networks of filaments and sheets, some dense enough to be opaque to visible light, others thin enough to see through. The three-dimensional structure of the region is complex, in ways that a flat map or a single photograph cannot convey. A landscape of matter and energy with hills and valleys and voids, shaped by millions of years of stellar activity. 1,000 light-years, 10% of the Orion Arm's traditional length estimate, still only a fraction of the arm's total extent, and already containing more objects, more complexity, more astronomical richness than any human institution has ever fully catalogued. Go further. At 5,000 light-years, the sphere encompasses roughly half the Orion Arm's length. The stellar population within this volume runs into the billions. Billions of individual stars, each one a nuclear furnace, the majority of them orbited by planets. The Cygnus star-forming complex, that powerhouse of stellar birth 4,000 to 5,000 light-years from Earth, falls at the boundary of this volume. Massive stellar associations containing some of the most luminous stars in our region of the galaxy are distributed throughout this space. Supernova remnants from explosions that occurred thousands of years ago are still expanding through the interstellar medium, their shockwaves heating and compressing the gas they encounter. Vast cold molecular clouds, dense reservoirs of hydrogen gas, not yet warm enough to begin star formation, drift through the arm in irregular shapes, ranging from a few light-years to hundreds of light-years across, waiting for some perturbation to trigger their eventual collapse. At 10,000 light-years, you have encompassed the full traditional extent of the Orion Arm in one dimension. You have taken in the entire structure from one end to the other in length, though its width extends for another 1,700 light-years or so on either side of the Sun's position. And within that volume, the contents are staggering. Let me make the most concrete comparison available. The total volume enclosed by the Orion Arm, using the traditional estimate of 10,000 light-years long by 3,500 light-years wide by roughly 1,000 light-years thick, accounting for the finite vertical extent of the galactic disk in our region, is approximately 35 billion cubic light-years. 35 billion cubic light-years. That is the physical volume of the structure those diagrams compress into 3 centimeters on a page. Now consider the volume of space that humanity has actually explored, the region through which we have sent spacecraft, where human-made objects have physically traveled, extends approximately 24 light-hours from the Sun in the direction of Voyager 1, our most distant probe. The volume of a sphere with a radius of 24 light-hours is approximately 0.00002 cubic light-years, and that generous estimate assumes the sphere is uniformly explored in all directions, which it is not. The ratio between the volume of the Orion Arm and the volume of space humanity has explored is a number with more than 30 zeros after the decimal point before a significant digit appears. We have not explored a small fraction of the Orion Arm. We have not explored a tiny fraction. We have explored a fraction so vanishingly small that it is mathematically indistinguishable from zero. Every mission in the history of human spaceflight, every orbiting satellite, every planetary probe, every crewed mission to the moon, every Mars rover, the entire sum total of human activity beyond Earth's atmosphere, all of it together has traversed a volume of space that rounds to nothing when compared to the arm we live in. We have taken one step out of the front door and declared ourselves explorers of the neighborhood. There is no other way to say this that does it justice. We are at the very beginning of understanding the structure we inhabit, not partway through, not well advanced, at the very beginning. The instruments we are building, the telescopes and spacecraft and data systems that represent the most sophisticated technology our civilization, are allowing us to see the Orion Arm for the first time with anything approaching real clarity. And what they are showing us, consistently, is that it is larger, more structured, more complex, and more extraordinary than any previous generation of scientists could determine. The local bubble tells us that even the immediate vicinity of the Sun has been shaped by dramatic events we are only now piecing together. The Gaia measurements tell us that the arm extends further than we thought. The planet statistics from Kepler tell us that billions of worlds orbit inside it, and the simple physics of light travel time tells us that different parts of the arm exist, from our perspective, in different eras of history. When we observe a star-forming region 4,000 light-years away in the Orion Arm, we are seeing it as it was 4,000 years ago, in the time of ancient Egypt's New Kingdom. Whatever is happening there at this moment, we will not know for another 4,000 years. The arm is so large that its parts are causally disconnected from each other on human timescales. Events at one end cannot be known at the other end for 10,000 years. This is what the Orion Arm actually is, not a thin bridge on a diagram, not a minor spur between grander features. A vast, dynamic, internally structured region of space, containing billions of stars and billions of worlds, shaped by billions of years of stellar birth and death, so large that its extremities lie in different historical eras, as seen from our vantage point, and so thoroughly unexplored that the entirety of human spaceflight amounts to a rounding error in the accounting of its volume. It is our home, and we have barely opened the front door. There is a law written into the fabric of the universe that no amount of technological progress will ever overturn. It is not a limitation of our current engineering. It is not a constraint that a sufficiently advanced civilization might find a way around with enough ingenuity and enough time. It is a fundamental feature of how reality is constructed, as basic and as non-negotiable as the existence of space and time themselves. Nothing that carries mass can travel at the speed of light. Nothing that carries information can travel faster than light. The speed of light is not a barrier waiting to be broken. It is the absolute ceiling of what the universe permits, built into the geometry of space-time at a level so deep that circumventing it would require reality to be structured differently than it is. Light travels at approximately 300,000 kilometers per second. In a single second, a beam of light covers a distance greater than the circumference of Earth 7 times over. In a minute, it travels 18 million kilometers. In an hour, over a billion. In a day, roughly 26 billion. In a year, 9.46 trillion. These are extraordinary speeds by any standard anchored in human experience. And yet, even at this extraordinary speed, crossing the Orion Arm takes 10,000 years. 10,000 years. Imagine you wanted to send a message to a civilization living near a star at the far end of the Orion Arm. Not travel there, not visit. Simply send a signal, a beam of light or a radio wave, both of which travel at the same speed, the maximum speed the universe allows. You compose your message and transmit it today, in this year, from Earth. That message departs at the speed of light and begins its journey. Your message will arrive at the far end of the Orion Arm in approximately the year 12,026. Whatever civilization receives it, if any receives it at all, will be as temporally distant from us as we are from the people who first began farming in the Fertile Crescent. If they respond immediately, their reply departs at the speed of light. It arrives back at Earth in approximately the year 22,026. A round-trip exchange of 2 messages, Nothing more than a greeting and a response, takes 20,000 years at the fastest speed the universe permits. Not 20,000 years of travel, 20,000 years of waiting for information, just words, just signals, 20 millennia for a conversation to complete one exchange. This is not a failure of imagination or a gap in our technology. It is the physical reality of the arm we inhabit. The Orion Arm is so large that the speed of light, the fastest possible means of transmitting anything, is effectively useless for communication across its full extent on any timescale that has meaning for a civilization. The arm is, in the most literal physical sense, too large for its own contents to know each other in real time. Consider what this means for the question of other civilizations. It is a question that has occupied human minds for centuries, and that has been examined with increasing scientific rigor over the past several decades. The universe is vast. The Orion Arm alone contains hundreds of millions of potentially habitable worlds. The probability that Earth is the only place in this structure where chemistry organized itself into something living seems, to many thoughtful people, vanishingly small. Perhaps other civilizations exist somewhere in the arm. Perhaps some of them are technologically sophisticated. Perhaps some of them have been broadcasting signals into space for thousands of years, hoping that someone, somewhere, might be listening. Even if that is true, even if the Orion Arm contains other civilizations right now, the physical scale of the arm ensures that contact between them is extraordinarily difficult. A civilization broadcasting radio signals from a star 5,000 light-years away sent those signals 5,000 years ago. The civilization that sent them may no longer exist. It may have risen and collapsed and been replaced by something utterly different in the time those signals spent traveling toward us. When we receive them, we are not hearing a contemporary voice. We are receiving a message from a past so deep that 5,000 years ago, the city of Babylon had not yet been built. And if we respond, our reply will arrive 5,000 years from now, at which point, whatever remains of that civilization will be receiving a message from a past equally deep in their own future. Communication across even a fraction of the Orion Arm does not connect contemporaries. It connects civilizations separated by millennia, exchanging messages across gaps of time so large that the entire span of what we call history fits comfortably within them. The Orion Arm is not merely physically vast, it is temporally vast. Its spatial dimensions translate directly into temporal separations that make the arm, for all practical purposes of civilization and contact and shared knowledge, a collection of isolated worlds each living in its own era, each unable to know what is happening anywhere else in the arm, except by receiving light that is already ancient by the time it arrives. Now take one step further back, because the Orion Arm, enormous as we have established it to be, is still only one feature of the Milky Way, and the Milky Way is still only one galaxy. The Milky Way spans approximately 100,000 light-years from edge to edge. Its disk, measured at the level of the spiral arms, is thought to extend to roughly 100,000 light-years in diameter, though recent studies suggest it may be somewhat larger. Its total stellar population is estimated at somewhere between 100 billion and 400 billion stars, a range reflecting the genuine difficulty of counting stars you cannot see individually across the full extent of the disk. Its total mass, including the dark matter halo that extends far beyond the visible disk and constitutes the majority of the galaxy's gravitational mass, is estimated at roughly 1 trillion solar masses. We are, with the Orion Arm, examining a feature that spans about 10% of the galaxy's diameter. The remaining 90% extends outward from our position in every direction, filled with other arms, other spurs, other interarm voids, the dense stellar populations of the galactic bulge and bar, the sparse outer disk where the galactic structure thins and fades, all of it rotating, all of it evolving, all of it operating on timescales so long that the entire span of human civilization represents less than 1/1,000,000th of a single galactic orbit. The Milky Way itself sits within a gravitational grouping called the local group. This is a collection of roughly 80 galaxies bound together by their mutual gravity, spread across a volume of space approximately 10 million light-years across. Most of these galaxies are small, irregular or dwarf systems, modest collections of a few billion stars at most. But the local group contains two large spiral galaxies. The Milky Way is one. The other is the Andromeda Galaxy, designated Messier 31 inches, the catalogue compiled by the 18th century French astronomer Charles Messier. Andromeda sits approximately 2.5 million light-years from the Milky Way. 2.5 million light-years. The light you receive when you look at Andromeda on a clear autumn night, that faint smudge barely visible to the naked eye in the constellation of the same name, left its source 2.5 million years ago. When that light departed Andromeda, the genus Homo did not exist. The ancestors of modern humans were Australopithecines, small-brained bipedal primates living in Africa, whose cognitive capabilities were separated from ours by a gulf so enormous that comparing them to us is almost meaningless. The light you are seeing tonight from Andromeda is older than our entire genus, and Andromeda is our nearest large neighbor. It is the closest large galaxy to the Milky Way, the nearest equivalent structure, 2.5 million light-years away. There is something else about Andromeda worth knowing. It is approaching. The Milky Way and Andromeda are gravitationally bound to each other, and they are moving toward each other at roughly 110 kilometers per second. In approximately 4.5 billion years, they will collide, not in the explosive, catastrophic sense that the word collision might suggest. Galaxies are mostly empty space. When two galaxies merge, most of the individual stars pass by each other without directly colliding, the way two swarms of bees can merge without individual bees necessarily colliding. But the gravitational interactions will be profound. Stellar orbits will be dramatically disrupted. Gas clouds will be compressed by tidal forces and trigger enormous bursts of star formation. The two disk galaxies will distort into wild, irregular shapes as they pass through each other. Separate, fall back together, and over the course of 1 billion years or more, gradually merge into a single large elliptical galaxy. The Sun will survive this event almost certainly, though its orbit will be changed substantially, and it may end up in a very different part of the merged galaxy than it currently occupies. Earth, if it still exists, will still be here. The night sky will be spectacular beyond any description adequate to the sight, filled with the combined stellar populations of two merging galaxies, bright enough to read by from the light of hundreds of thousands of nearby suns. And from that transformed world, the structure we have been calling the Orion Arm will no longer exist as a coherent feature. It will have been disrupted, its stars scattered into new orbits by the gravitational upheaval of the merger. The address we have been examining tonight will have been demolished by the largest event in the history of the solar neighborhood since its formation. But that is 4.5 billion years away. For now, Andromeda approaches slowly, and the local group persists as a relatively stable gravitational community of galaxies. Beyond the local group lies the Virgo supercluster, sometimes called the local supercluster. This is a larger gravitational structure, encompassing the local group along with dozens of other galaxy groups and clusters, spread across a region roughly 110 million light-years across. The Virgo cluster itself, the dense central concentration of the supercluster, located about 54 million light-years from the Milky Way, contains more than 1,300 galaxies in a relatively compact region of space, 54 million light-years away. The light from the Virgo cluster that enters your eye on any given night departed its source 54 million years ago, when the dinosaurs had been extinct for only 10 million years and the earliest primates were only just beginning to diversify into the forms that would eventually produce something capable of noticing the light. The Virgo supercluster is itself a component of a still larger structure called Laniakea, identified and named in 2014 by a team of astronomers led by Brent Tully of the University of Hawaii. Laniakea is a supercluster of superclusters, a vast cosmic web of galaxies spread across roughly 500 million light-years and containing the mass of approximately 100 million billion suns. The name comes from the Hawaiian words for immeasurable heaven. 500 million light-years across, the Milky Way sits near the outer edge of Laniakea, toward its periphery, slowly drifting under the gravitational influence of the Great Attractor, a region of excess mass density near Laniakea's center that is pulling everything in the supercluster toward it at hundreds of kilometers per second. And Laniakea is one feature among many in the observable universe. The observable universe, the region from which light has had enough time since the Big Bang to reach us, spans approximately 93 billion light-years across. Within that volume, current estimates place the number of galaxies at roughly 2 trillion galaxies, each one a gravitationally bound system of billions or hundreds of billions, or in some cases, trillions of stars, each one separated from its nearest neighbors by millions of light-years of essentially empty space. The scale cascades without mercy. Start with the Sun, one star among hundreds of billions in the Milky Way. The Solar System, a tiny gravitational domain extending a few light-hours from the Sun. The Orion Arm, a feature 10,000 light-years long containing billions of stars, including the Sun. The Milky Way, 100,000 light-years across, containing the Orion Arm and all the rest of its spiral structure. The Local Group, 10 million light-years across, containing the Milky Way and Andromeda and dozens of smaller companions. The Virgo Supercluster, 110 million light-years across, containing the Local Group. Laniakea, 500 million light-years across, containing the Virgo Supercluster. The Observable Universe, 93 billion light-years across, containing Laniakea and trillions of comparable structures. At each step, the previous level shrinks to invisibility. The Orion Arm, which took this entire journey to properly characterize, which we have spent thousands of words establishing as a structure of genuine enormity, disappears into insignificance at the scale of the Milky Way. The Milky Way disappears at the scale of the Local Group. The Local Group disappears at the scale of Laniakea. Laniakea disappears at the scale of the observable universe. And the observable universe may itself be only a fraction of whatever exists beyond the boundary from which light has not yet had time to reach us. The scale never stops. It cascades outward in every direction, each level dwarfing the one below it by factors of thousands or millions, until the numbers become so large that even scientific notation begins to feel inadequate, and the human mind simply stops trying to picture what is being described and accepts instead a kind of abstract acknowledgement that the universe is very, very large. But here is what this cascading scale actually means, and it is something different from the simple conclusion of vastness that most people arrive at when confronted with these numbers. The cascading scale means that every level of the hierarchy, from the smallest to the largest, is genuine. Every level is real. The Orion Arm is not rendered insignificant by the existence of the Milky Way, any more than the Amazon River is rendered insignificant by the existence of the Pacific Ocean. Each level is what it is. The Orion Arm is 10,000 light-years of space containing billions of stars and billions of worlds, and the entire history of human existence. That is true regardless of how large the Milky Way is, regardless of how large Laniakea is, regardless of how large the observable universe is. The existence of something larger does not diminish the reality of something smaller. It only provides context. And the context provided by the larger scales is not that the Orion Arm is negligible. It is that the universe operates at scales so extreme that our evolved intuitions about size and significance cannot be trusted at any level of the hierarchy above the immediately human. We are small. The Orion Arm is large. The galaxy is vastly larger. The universe is vastly larger still. All of these things are simultaneously true, and none of them cancels any of the others out. What the cascading scale does provide, if you allow it to work on you honestly, rather than simply overwhelming you into numbness, is a particular kind of perspective. The perspective of a creature that has managed, through the application of mathematics and physics and careful observation, to comprehend a universe it had no evolutionary reason to understand. We did not need to know the size of the Orion Arm to survive on the African savanna. We did not need to understand galactic structure to find food and water and avoid predators. The knowledge serves no immediate practical purpose in the day-to-day business of biological survival. And yet here we are, having built the instruments and developed the mathematics and taken the careful measurements needed to determine that the arm we live in is 10,000 light-years long, that it contains billions of worlds, that it sits between two major spiral arms, each 3 to 4 times its length, that it is embedded in a galaxy 100,000 light-years across, that galaxy is one of 2 trillion in the observable universe, and that the observable universe may itself be only a fraction of all that exists. We figured all of this out from a single small rocky planet, orbiting one ordinary star in the inner edge of a secondary spiral feature of one galaxy among trillions. We measured the universe from a point so small within it that it registers as nothing on any map that honestly represents the scales involved. That is not a cause for despair. That is extraordinary. That is perhaps the most extraordinary thing about us. There is a word that appears consistently in discussions of cosmic scale, and it is worth examining carefully before we bring this journey to its close. The word is insignificant. It appears in popular science writing, in documentary narration, in the reflexive conclusions that many thoughtful people draw when they genuinely absorb the numbers we have been examining. We are insignificant, the argument goes, because the universe is so vast and we are so small within it. The Orion Arm is insignificant because the major spiral arms are larger. The Milky Way is insignificant because Laniakea contains hundreds of thousands of comparable galaxies. Everything is insignificant because the observable universe contains 2 trillion galaxies and will exist for trillions of years after the last star has burned out and the last black hole has evaporated into radiation. This conclusion feels logically inevitable. It presents itself as the honest reckoning, the mature response to the numbers, the appropriate humility of a species that has finally understood its true place in the cosmos. But it is wrong. Not emotionally wrong, in the sense of being an uncomfortable truth that we would prefer to avoid. Logically wrong. It confuses size with significance and treats physical scale as though it were the only dimension along which importance can be measured. Size and significance are not the same thing. They have never been the same thing. A thought is not physically large. An act of kindness occupies no measurable volume. The moment of recognition when a mathematical proof resolves into clarity takes up no space that any instrument can detect. Love, grief, curiosity, wonder, the experience of standing outside on a clear night and looking up at a band of pale light and asking what it is, none of these have physical dimensions. None of them can be compared to the Orion Arm and found wanting on the basis of spatial extent. The universe is enormous. You are small within it. Both of these things are true. Neither of them says anything about whether you matter. The category of mattering is not a physical measurement. It is not something that telescopes can quantify or that spacecraft can map. It belongs to a different domain entirely, one that the numbers we have been examining simply do not address. But there is something more specific to be said, something that goes beyond the philosophical point about the incommensurability of size and significance. It concerns what you actually are, in physical terms, in relation to the Orion Arm, because you are not merely a small object existing inside a large one, the way a pebble exists inside a mountain or a water molecule exists inside an ocean. The relationship is more intimate than that, more surprising, more profound. The atoms in your body were forged inside stars. This is not a metaphor. It is not an approximation or a poetic elaboration of something more prosaic. It is a precise description of the nuclear physics that produced the matter you are made of. The hydrogen in your body, the most abundant element in the universe, was produced in the first few minutes after the Big Bang, when the universe was hot and dense enough for protons to fuse. But hydrogen alone cannot build a living thing. The carbon in your organic molecules, the oxygen you breathe, the nitrogen in your proteins, the phosphorus in your DNA, the calcium in your bones, the iron carrying oxygen through your blood at this very moment. None of these existed in the early universe. They were synthesized later, inside stars. In the cores of massive stars, nuclear fusion proceeds through a sequence of reactions that builds progressively heavier elements. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into neon and magnesium and silicon and sulfur, and eventually iron. The process stops at iron because fusing iron requires more energy than it releases, and at that point, the star's core collapses. The collapse triggers a supernova explosion that disperses all of the elements synthesized over the star's lifetime, along with additional heavy elements produced in the extreme conditions of the explosion itself, into the surrounding interstellar medium. Over millions of years, that enriched gas drifts and mixes with the rest of the material in the spiral arm. It becomes part of the molecular clouds, floating through the Orion Arm, the cold reservoirs of gas and dust from which new generations of stars and planetary systems form. When one of those molecular clouds eventually collapses under its own gravity to form a new star, the planets that coalesce from the leftover disk inherit the chemical composition of the cloud, including all of the heavy elements scattered by previous generations of stellar explosions. That is how the Sun formed approximately 4.6 billion years ago. That is how Earth formed from the disk of material surrounding the young Sun, and that is how the atoms in your body came to exist. They passed through the interiors of stars that lived and died inside the Orion Arm millions or billions of years before the Sun was born. They were scattered by supernova explosions into the interstellar medium of the arm. They drifted through space as part of a molecular cloud. They collapsed with that cloud into the solar system. They assembled into the rocky planet we call Earth. They participated in 4 billion years of geological and biological processes. And eventually, through a sequence of events that remains only partially understood, they organized themselves into living things, and those living things evolved over billions of years into something capable of asking where the atoms came from. You are made of Orion Arm material. You are not a visitor to the arm, not an observer of it from outside, not a consciousness that somehow arrived in this structure from somewhere else. You are assembled from the arm's own substance. The carbon in every cell of your body was produced inside a star that orbited the galactic center somewhere in this region of space. The iron in your blood was synthesized in the core of a dying star that exploded long before the Sun existed. You are the Orion Arm examining itself. You are the structure becoming curious about its own nature and developing the instruments and the mathematics to measure what it is. This is not a small thing. This is not a fact diminished by the arm's relative size compared to the Perseus or Scutum Centaurus arms. The Perseus arm, as far as we know, has not produced anything that can measure its own extent. The Scutum Centaurus arm, as far as we know, has not generated anything that wondered where it came from. The Orion Arm has. In at least one location, in one solar system, on one rocky planet, the matter of the arm organized itself into creatures that looked outward and began to comprehend the structure around them. Whether this has happened elsewhere in the arm, we do not know. Whether other worlds within those hundreds of millions of potentially habitable zones have produced their own curious, measuring, wandering forms of matter, we cannot say, but we know it happened here. We are the evidence, and the fact that it happened at all, that the universe is the kind of place where matter can do this, is a fact about the universe that has no analog in any measurement of physical scale. So let us return now to the image that began this journey, the galaxy diagram, the one you have seen countless times, the one that shows the Milky Way in its entirety, arms sweeping outward from the glowing center, everything color-coded and labeled, and somewhere between two of the larger features, a thin, modest-looking sliver with an arrow or a label or a small marker indicating your location. You are here. You have spent this entire journey learning what that label actually means. Not the proportional fact that the Orion Arm is shorter than the Perseus Arm or less massive than the Scutum Centaurus Arm, though both of those things are true, but the absolute fact, the physical reality that the diagram, by its nature, cannot convey. Those few centimeters of ink on the page contain 10,000 light-years of space. They contain a structure that light, the fastest thing in the universe, requires 10 millennia to cross. They contain billions of stars, each one a nuclear furnace, converting matter into energy, most of them orbited by planets. Many of those planets rocky, some of those rocky worlds sitting in orbits where liquid water could exist on their surfaces. They contain the Orion Nebula, where new stars are being born right now. They contain Betelgeuse, a dying stellar giant that will eventually explode with a brilliance visible in daylight from Earth. They contain the remnants of stars that exploded thousands of years ago, their debris still expanding outward through the interstellar medium. They contain the local bubble, a cavity blown by ancient supernova whose shockwaves triggered the formation of the very stellar nurseries we study today. They contain every star you have ever seen with your naked eye, every exoplanet ever detected, every astronomical object ever named. And they contain you, every human being who has ever lived, every civilization that has ever risen and fallen, every word ever written and every thought ever formed. All of it has occurred inside those few centimeters of ink, inside this one feature of the Milky Way, inside this secondary structure that galaxy diagrams have been inadvertently teaching people to dismiss for as long as such diagrams have existed. The next time you encounter one of those diagrams, the reaction it should produce is not the familiar mild acknowledgement that follows from having seen it many times before. It should be something closer to the feeling you get standing at the edge of a cliff, looking down into a canyon whose full depth you cannot see. The slight vertiginous recognition that you are standing at the boundary of something larger than your eyes can properly communicate to your brain. Because the label on that diagram is not pointing at something small, it is pointing at 10,000 light years. It is pointing at billions of worlds. It is pointing at the structure that produced you from its own substance and has been carrying you through the galaxy at 230 kilometers per second for your entire life without your ever needing to think about it. The Orion Arm has been your home for every moment of your existence. It was your home before your existence, when the atoms that would eventually become you were scattered through its interstellar medium. It will be your home long after your existence, when those atoms return to the gas and dust between stars and drift toward whatever comes next. The Arm's timescale dwarfs your own, the way the Arm's spatial scale dwarfs the room you are sitting in right now. You are a brief configuration of its matter, a temporary arrangement of atoms that happens to be self-aware, looking out through instruments made of more of its atoms at the structure you are embedded in and beginning, slowly, to understand it. That is what those few centimeters on a galaxy diagram actually represent. Not a minor spur, not a footnote, not an unremarkable connector between more impressive features. Everything. There is a clarity that settles in when you allow the full weight of this to land. Not the numb, distancing clarity of a number too large to feel, but something different, a kind of recalibration. The ordinary world does not change. The distances to the grocery store and the workplace remain what they were. The concerns of daily life retain their reality and their urgency. But behind all of it, underneath the immediate and the practical and the pressing, there is now this. The knowledge that you are riding through the galaxy inside a structure 10,000 light years long, assembled from the debris of stars that died before the sun was born, on a planet that formed from the same molecular cloud that gave rise to the sun, in an arm of the Milky Way that diagrams have been misrepresenting for as long as there have been diagrams. The knowledge changes the context without changing the content. And changed context, for creatures like us, changes everything. On a clear night, far from city lights, you can see the Milky Way, not the whole galaxy, not a view from outside, but the inside of it, looking along the plane of the disk where the concentration of stars is greatest. It appears as a pale, diffuse band of light arching across the sky, soft at the edges, slightly brighter toward the center, interrupted by dark rifts where dense dust clouds block the light from more distant stars. It does not look like much. It does not announce itself as the interior view of a barred spiral galaxy, 100,000 light years across. It looks, to eyes evolved for a very different purpose, like a smear of faint light against the dark. But that smear is the Orion Arm seen from within. The combined glow of billions of stars spread across thousands of light years, blurred by distance into a continuous luminous band. When you look at it, you are looking at your neighborhood. You are looking at the structure that contains your sun, your planet, your entire civilization, and the full span of human history. You are looking at the thing made of which you are also made, seeing it with eyes assembled from its own atoms, comprehending it with a brain that grew from the same stellar debris that fills the space between the stars you are looking at. Every culture that has ever looked at that pale band and wondered what it was asking the right question. They did not have the tools to answer it. They constructed the best explanations available to them with what they had. The ancient Greeks wove it into the mythology of Hera and spilled divine milk. The Aboriginal Australians of the continent now called Australia saw it as a river running through the sky, the dark spaces between the bright regions interpreted as the bodies of celestial animals. The San people of southern Africa understood it as the embers of ancient campfires thrown across the heavens. The Lakota people of the North American plains knew it as a road for the spirits of those who had passed from this world. None of them knew they were looking at the interior of a spiral arm in a barred spiral galaxy. None of them knew the light was billions of years old, that it had traveled thousands of light years to reach them, that the structure it came from was so large that light itself would need 10 millennia to cross it. But they looked, they wondered, they built stories around the wondering, because that is what human beings do when they encounter something that exceeds their current capacity to explain. The wondering is the constant, the explanations change as the tools improve. But the act of looking up at that pale band and feeling that something important is being witnessed, something that exceeds the ordinary scale of daily existence, that act is as old as our species and as fundamental to what we are as anything in our biology. Now you know what you are looking at. You know the name of the structure, its dimensions, its contents, its position in the galaxy, its history of supernova and star formation, and the slow, patient accumulation of stellar generations, each enriching the interstellar medium with the heavy elements needed for the next. You know that it is not small. You know that the diagrams have been lying to you by compression, and that the truth is 10,000 light years and billions of worlds and an age stretching back through a substantial fraction of the universe's history. And knowing this, looking up at that pale band becomes a different act than it was before. The light entering your eyes is older than human civilization. It traveled 10, 100, 1,000, 5,000 light years to reach you, carrying information about stars you will never visit, about worlds you will never see, about regions of the arm that exist in a different historical era from your perspective, because the light travel time between here and there is longer than the span of recorded human memory. You are receiving messages from your own neighborhood that were sent before you were born, before your parents were born, before every human being alive today was born, before every civilization currently existing had been founded. The arm is sending you its light continuously, and you are receiving it. And the gap between transmission and reception is measured not in seconds or minutes or years, but in centuries and millennia. That is the Orion Arm. That is your home. That is the structure those diagrams have been drawing in a few centimeters for as long as galaxy diagrams have existed, quietly understating its scale with every printing, every projection, every screen on which it has appeared. It is 10,000 light years long. It contains billions of stars and billions of worlds. It produced you from the debris of its own dead stars. It has been carrying you through the galaxy at 230 kilometers per second since before you had the capacity to notice. And it is still there tonight, above you, visible on any clear dark night as a pale diffuse glow that stretches from horizon to horizon. Go outside and look at it if you can. Let the light from billions of stars cross thousands of years to land on your eyes. Stand inside your neighborhood in the galaxy and look along its length and understand, in whatever way understanding is possible for creatures of your scale and duration, what you are standing in. It is vast beyond any comfortable comprehension. It is ancient beyond any scale your life has equipped you to feel. It is the source of every atom in your body and the destination of every atom in your body when the temporary arrangement that is you eventually returns them to the interstellar medium. It is not small. It was never small. It only ever appeared that way on a page. The pale light above you is not a smear in the dark. It is 10,000 light years of history, billions of suns, hundreds of millions of worlds, and the answer to the question of where you come from. It is home, and it is extraordinary.